the last problem in this unit, problem 3.14. Consider the sequence defined by x sub n plus 1 is equal to x sub n times 1 plus x sub n over 1 plus 2 times x sub n, when x sub 1 is 1. Okay. Now the first part is to prove that x sub n is greater than 0 for all n. Okay, that's easy. Again, we use induction. Okay. So we have x sub n is greater than 0 for all n. Well, the first one is to try and check for n equals 1. X sub 1 is 1, is greater than 0. Great. Now assume x sub n is greater than 0 for some value of n. Now what happens with x sub n plus 1? Is it greater than 0? Now we have x sub n plus 1 is x sub n times 1 plus x sub n over 1 plus 2 times x sub n. Okay, so if x sub n is greater than 0, then this thing is greater than 0. Okay. Now this factor again, if x sub n is greater than 0, it's greater than 0. And this factor too is greater than 0. So every factor is greater than 0. This is greater than 0. So we have just proven by induction that x sub n is greater than 0 for all n in the natural numbers. Okay. Now let's go for part B. Prove that the sequence is monotonically decreasing. Okay. We subtract x sub n plus 1 minus x sub n. We have x sub n times 1 plus x sub n minus, and then if we want to write this in the same fraction, we have x sub n minus 2x sub n squared. Okay, and this is just x sub n plus x sub n squared, and if you realize this is x sub n minus x sub n, and then in the numerator you have minus x sub n squared, 1 plus 2xn. Okay, the denominator we know it's positive because x sub n is positive, and then numerator is a negative square, which is, and a square is always positive, so this is negative. Okay, so the difference between x sub n plus 1 and x sub n is smaller than 0. That means the sequence is decreasing. Okay, and then lastly, the limit of the sequence, again, we take limits in both sides of the equation. We call x the limit when n goes to infinity of x sub n. So this is 1 plus x, 1 plus 2x, and because we know this is positive, we can multiply both sides by it. So then we have x plus 2x squared is equal to x plus x squared. X and x cancel each other out, and you have x squared is equal to 0. X is 0. That's the only possible solution. And it makes sense. It starts at 1. The sequence is monotonically decreasing, and it goes to 0. Okay, it's bounded by 0. So that's the end of the proof.